Okay, we mentioned Jakob Bjerknes a few times. So let's look at what actually he proposed. As we said, Gilbert Walker had found the pressure oscillation between Darwin and Tahiti, and he said when they go in the opposite direction of the normal conditions, i.e. Tahiti becomes anomalously weak sea level pressure, and Darwin gets anomalously high surface pressure, then there tends to be a monsoon drought and famine. Drought and famine are not the same, but we'll not go into that here. What Bjerknes did in the 1960s was to show that if you perturb the sea surface temperatures in the East Pacific, that tended to weaken the east-west sea surface temperature gradient. Remember that the east is cooler by 8 to 10 degrees from the west, so you have a sea surface temperature gradient. Cold temperatures, high sea level pressure; warm temperatures, low sea level pressure. You are in the deep tropics, so Coriolis is weaker, so you can, in fact on the equator it's zero, so you can drive a zonal wind with this pressure gradient, right? So if you change the pressure gradient, you're going to change the winds, which means you're going to change the upwelling, which further changes the temperature, further changes the winds, and so on. So he proposed that for whatever reason, if you perturb the temperatures in the East Pacific, for example, if you warmed it, you would weaken the east-west temperature gradient, you would further weaken the trade winds, which would reduce the upwelling, and it would further warm the sea surface temperature. Since this is a loop, you can start anywhere, because we don't know exactly what happens first always. So if for some reason trade winds weakened, it would reduce the upwelling, it would warm the East Pacific temperatures, sea surface temperatures, deepen the thermocline, and the sea surface temperature gradient from the east to west would weaken, and it would further weaken the trade winds, and so on. So this is what happens during an El Nino. Something happens in the system which sets off this loop, and it keeps growing till some waves come and return the system to normal, or the warm water that had built up would be exhausted, and then trade winds begin to pick up again, and so on. And a similar feedback happens during the La Nina. So again, starting anywhere in the loop, if you somehow enhanced the trade winds, and that increases the upwelling, it would cool the sea surface temperatures in the east, it would increase or strengthen the east to west temperature gradient, which would further strengthen the winds, pressure gradient, and then the wind, and that would further enhance upwelling, and so on. So this is what happens during the La Nina. The trick is, of course, that you can usually observe these only after they have started. And if you want to make accurate predictions, obviously you have to be able to say when it will happen. In general, the El Nino prediction skill is very good, which means models can predict almost 6 months ahead of time, but as I said, that's because this loop has already started. To extend the time scale of prediction to predict it 12 months before and so on, you would need to be able to figure out which of these processes starts and why. Okay, that's not easy because we don't always know what the processes are. Now, there are various indices that are defined to identify El Niños. We said El Niño, the main feature was warming in the East Pacific, but we will soon see that the East Pacific doesn't necessarily warm with every El Nino. So some people use the perturbation of the West Pacific convection as an index. Why is that? Because if you remember the outgoing long wave radiation, the deep convection and the tall clouds have cold temperatures at the top, and the local dip in the OLR in the deep tropics. So if you can use OLR as an index of the movement of the deep convection, then maybe that'll tell you something as well as to what will happen in terms of the Bjerknes feedback and the growth of an El Nino. So this is some oceanic Nino index, which averages in the deep tropics, in the Pacific, the sea surface temperature anomalies, and it looks at below normal. This black line here at 0 is the long-term normal situation. If it gets colder than normal, that's a La Nina. If it's warmer than normal, that's a El Nino. And those El Ninos can be weak when they are in this range of ONI index less than 1. They can be moderate between 1 and 1.5, and strong when they reach 2 and above. And you can see that there have been a few strong El Ninos in the recent decades. There are probably some that happened before that we haven't recorded as well as we recorded the 82-83 El Nino, which was one of the first ones recorded just after El Nino theories began to come together, and El Nino scientists, well, they were not yet El Nino scientists, I guess, started to look at the data, and the first satellite data was sending very, very warm temperatures in the East Pacific, much warmer than normal, and people who do the satellite data thought this was an error in measurements, so they actually were throwing out the data thinking something is wrong. So 97-98 got very strong. Why do we say 82-83, 97-98, 15-16? Because El Ninos happen during, the peak happens during November, December, January, or December, January, February. So it goes from one year into the next year because the winter crosses the calendar year across December, right? So that's why we typically tend to associate them with 2 years. And as we said, El Nino lasts for 9 to 12 months. This whole process of discharging the warm water moving east, convection happening, returning back to normal, all takes 9 to 12 months. So approximately 15 years or so here. It took longer than that. There seem to be these very strong El Ninos. Again, not fully explained why that is. If you just want to visually look at it, it looks like there are periods where there are more La Ninas, and maybe there are periods where there are fewer La Ninas, and maybe there are more El Ninos and fewer El Ninos, and so on. This is important to understand that El Nino is not a very regular oscillation. As you can see, sometimes it happens back to back here in 53, 54, I think, and there are some here that went from 91 to almost 94, and another one here. So the periodicity is not regular, which raises the question of whether it's just an oscillation. If so, why is the period not constant, or whether it's a system that needs a kick from somewhere that then goes into an oscillation, is damped, so it dies out. All these questions are still kind of open questions. Okay, so we will see that El Ninos have flavors, which means sometimes it does warm strongly in the east, but sometimes not so strongly in the east. There is the hammering sound coming there from construction of a metro line. I hope that's not getting recorded here, but I'll test it soon. So El Nino is a complicated, a very detailed topic. We are going to have just a few podcasts to get a sense of the processes. We won't say much about predictions and so on, but we will look at the response of El Nino very briefly to global warming, because that controls some important evolutionary features of global warming, which we will look at.